Look up at the night sky and you might see a bright streak of light. It looks like a meteor. In reality, that is a highly advanced satellite breaking apart and vaporizing as it hits the upper atmosphere. This chart tracks Starlink satellites in orbit since 2019. Notice this sharp drop. Between December 2025 and May 2026, SpaceX deliberately incinerated 260 working satellites. Following the downward dotted line, another 349 are queued for the same fate. It is easy to assume this is the result of a hardware failure, or perhaps a solar flare taking out the network, but the engineering logs tell a different story. This was a highly coordinated, intentional decommissioning executed directly by SpaceX operators. The world's largest satellite internet provider operates on a model of upgrade by incineration. To understand why they do this, we have to look at what this constant cycle of destruction actually costs us. Traditional aerospace engineering treated satellites as monuments. Multi-billion-dollar machines were built to hover in geostationary orbit for 15 to 20 years, completely untouched. This comparison table breaks down that traditional model against SpaceX's low Earth orbit, or LEO, megaconstellation. Where older satellites lasted decades, Starlink operates on a 5-year operational lifespan. The environment in low Earth orbit is brutal. Satellites pass from boiling sunlight to freezing shadow every 90 minutes. That continuous thermal cycling gradually degrades onboard batteries and solar arrays. If operators wait for a satellite to completely lose power before taking action, they lose the ability to steer it. It becomes a dead 500-pound kinetic weapon, traveling at hypersonic speeds through a crowded orbital highway. To prevent that, SpaceX uses a strategy called constellation attrition. At the first sign of telemetry decay, long before a total failure, they actively remove the satellite from the network. They treat space infrastructure the same way a carrier treats cell phone towers. It is disposable hardware built for rapid replacement. The old hardware is dying right now to make room for a hardware leap. This is a standard Starlink consumer dish. The basic broadband capabilities of early iterations paired with hardware like this were quickly outgrown by the demand for low-latency data. We can see the physical differences on this side-by-side scorecard. A Generation 1 Starlink weighed roughly 260 kilograms and acted as a basic signal relay. The incoming Generation 2 and Block 3 hardware weigh upwards of 1,200 kilograms. Looking down at the expanded payload capabilities, that extra mass allows for localized orbital edge computing. The satellites can process data natively in space. They also host highly encrypted military payloads for programs like Starshield. Because these new units are so massive and complex, physically retrieving the older, smaller satellites from orbit is an economic and physical impossibility. Deploying this much heavy hardware requires a continuous launch cadence, leaning on reusable Falcon 9 and Starship vehicles to fill the sky. To transition from basic internet relays to a network of orbital supercomputers, SpaceX is physically burning its past to deploy its future. The disposal phase officially begins when a satellite actively commands its own descent out of the operational network. To pull this off, the spacecraft fires its onboard krypton or argon-fed Hall-effect thrusters, pushing against its direction of travel. As it lowers into the upper atmosphere, intense friction converts its kinetic energy into raw thermal energy, vaporizing the chassis in minutes. Federal regulators require mega-constellation operators to maintain a post-mission disposal reliability rate of at least 95%. You have to prove you can clean up your own mess. We know SpaceX is complying because they submit their engineering logs directly to the Federal Communications Commission, the authority overseeing these orbital metrics. Those logs reveal an active disposal reliability rate exceeding 99% within a 6-month window. A reliable automated propelled Deorbit sequence is the only proven method to avoid the Kessler syndrome, a cascade of orbital collisions, and keep low Earth orbit safe for future missions. But keeping orbit safe creates a terrestrial trade-off. We have to look at what happens to the Earth when hundreds of heavy metal objects are vaporized annually. This life cycle flowchart tracks the physical transformation of the satellite during re-entry. A solid aluminum chassis does not vanish into nothingness. The extreme heat transforms it into a cloud of microscopic aluminum oxide, or alumina. As the chart shows, those alumina particles do not fall to the ground. They accumulate and trap themselves within the stratosphere layer above the Earth, where they linger for decades. Atmospheric scientists point to two risks from this accumulation. The illumina alters planetary albedo, how the Earth reflects solar radiation, and it acts as a catalyst for chemical reactions that destroy ozone molecules. This has triggered a policy battle. Environmental advocacy groups are pushing to revoke the NEPA categorical exclusion, a rule that has historically exempted space launches from environmental impact statements. Pressure is mounting on federal accountability bodies to weigh the environmental impacts of megaconstellations against technological progress. The direct trade-off for keeping physical space free of debris is the steady, unregulated chemical pollution of our upper atmosphere. If we step back from the specific hardware, we can evaluate the philosophy driving this era of space technology: raw iteration speed. This quadrant chart maps megaconstellations. We weigh iteration speed on the horizontal axis against environmental footprint on the vertical. Starlink's Generation 2 lands deep in the extreme upper right quadrant, representing the extreme of modern space strategy: high capability paired with a significant physical footprint. This model serves tech optimizers, consumers demanding uninterrupted global bandwidth, and defense departments needing encrypted data. For those audiences, the strategic decision to vaporize old hardware to enable the Gen 2 leap provides a significant upgrade in global utility. But the people left tracking the fallout, atmospheric scientists, environmental policymakers, and aviation regulators, have strong reasons to remain wary of this model. Federal aviation authorities are caught squarely in the middle, forced to balance the demands of rapid launch licensing against emerging environmental science. This debate directly involves the literal atmospheric shield of our planet. Regardless of the ongoing regulatory debates on Earth, the cadence of aerospace innovation and satellite deployment is only accelerating. The transition to Generation 2 shows SpaceX rotating through spacecraft generations at the same speed as the consumer electronics market. The ultimate boundary of this progress may be Earth's capacity to absorb its exhaust.